The scientific revolution starts now.
This is the Sci-Fi Podcast.
Let us see in the dark.
Hello, I'm Dr. Ed Bryant. I'm a researcher at the Mullard Space Science Laboratory, which is part of University College London in the UK. I've been working there for a year after finishing my PhD, which was at Warwick University up in the Midlands. And my research focuses on primarily the discovery of new exoplanets, so planets around stars that aren't the sun, mainly through the observation of exoplanet transits, which is where the planet will pass sort of in front of its host star as viewed from Earth, and we see a sort of dimming in the light, in the brightness from the star, and we can use that to infer or to discover that there's a planet orbiting that star. And so the work that I did recently was a sort of systematic search for these giant planets. So these are planets similar in size to Jupiter and Saturn, so large gaseous planets with host stars that were very low in mass, so between about 60% the mass of the sun and below. We searched around stars all the way down to sort of 20-30% the mass of the sun. And the reason why, and what we found in this search, was that these giant planets around these low mass stars are much rarer than they are around stars like the sun. But we do have some sort of confirmed planets and some more planet candidates down around these low mass stars, as low mass as 40%, even a candidate down to 20% the mass of the sun. And what's really exciting about this is that these low mass stars, based on the current predictions from the formation theory, it should be much harder for them to form these giant planets. These planets should be much rarer around these stars, but almost when you get down to these very low masses, around 30-40% the mass of the sun, lots of the theories predict that these planets should just not be able to form anymore. The stars are so low mass that the protoplanetary disks that they host are themselves very low mass, and you just can't build up these very giant planets. And so my discovery is that among other discoveries, that these giant planets do exist for these low mass stars, and these low mass stars clearly can form these giant planets, albeit very rarely and probably in quite extreme circumstances, is very exciting in terms of understanding how planets form in the universe.
It's really interesting how fast the planetary sciences have been on the move with, compared to other sciences, I think, that are in the headlines. It seems like, particularly this exoplanet project, when was the last time? I feel like it was maybe only 20 years ago that we were first able to see exoplanets. And so much of our planetary formation science was based on our solar system alone.
Absolutely, yeah. I mean, the first discovery of a exoplanet around a star like so around a main sequence star, so where stars spend most of their lifetime. The first discovery of a planet around a different star was only in 1995, so less than 30 years ago. It was 51 Pegasi b. But yeah, and you're exactly right. Up until then, before then, all our knowledge of planet formation was yet based on the solar system and the solar system planets. And what we saw, and people came up with some very clever theories that sort of came up with explaining the solar system really well, sort of what Jupiter and the gas giant planets form further out, the terrestrial planets form in, and people generally believe that planets formed where they were. But then we discovered 51 Peg, or I didn't, but people did back in 95, and it was found to be a Jupiter-sized planet in about a 4-day orbit around its star. And all of a sudden, everything we knew about planets changed overnight, more or less, because we suddenly people had to come up with ways of explaining how these giant planets could form and get so close to their star. And yeah, ever since then, so it seems that as it's such a new field, but we have all this technology in terms of space telescopes, very powerful telescopes, we have been able to make these advances much more quickly than perhaps other fields were able to. And it seems that every couple of years some new sort of weird exotic planetary system comes out that we never even thought of we'd see before and changes what we think we knew again.
So maybe we can go back to that first discovery. You said there was, it was PEG?
It was a 51 Pegasi B. Was the
51
first.
Pegasi B. Okay, so 51 Pegasi B, you realize that there's this hot Jupiter type of condition. How do people react? So you have a gaseous planet that is close to the sun and has this very, very short orbit. It breaks the paradigm of how these things form. What are the reverberations through the community? How does the theory get shifted? How do people account for it?
Yeah, so so 51 Pegasi B was obviously it was discovered a year before I was born. So it's actually sort of my life sort of tracks. I'm as old as the study of exoplanets, which is also kind of fun to think about. But yeah, I think in the time, a lot of people were looking for these planets. There were lots of teams all over the world trying to find these planets. And I think some of them just hadn't even considered that a planet could be that close to a star. And so they were looking for these planets through the radio velocity method. So they were monitoring the motion of a star due to the orbit of the planet around it, through measuring the Doppler shift of the light from the star.
So basically, the star wiggles a little bit when the planets tug on it as they go around, and you can see that.
Yes, no, exactly. Yeah, the star and the planet both sort of orbit the center of mass of the two of them. So yeah, the star does its own smaller orbit, and you can monitor that by studying the change in the light from the star and the wavelength that you observe. And then you get sort of 1 point a night per star, really, and so people were waiting, thinking they would have to wait months to find these planets, but then suddenly people started realizing that you could find there were these planets at 4 days, 3 days, 5 days, and then all of a sudden everything changed, and talking about the paradigm shift, and people suddenly realized that perhaps the solar system wasn't the blueprint and the only way you could have a planetary system. There were these hot Jupiters, as they came to be known. And they basically started coming up with these theories about how, as well as forming sort of while these planets likely did form, one of the main theories is that the planets do form sort of further out, sort of closer to where Jupiter sort of currently resides, but then they migrate in towards the star. And then various theories came up about how these planets could migrate and move through, either through sort of, if they're still forming and the protoplanetary disk is still there, then through interactions and friction with the gas in the disk, they can sort of lose angular momentum and start spiraling in towards the star, start moving their way in. Or if you have two stars quite widely separated with a planet orbiting one of the stars, then you can get gravitational interactions between the outer star and the planet, and then this can sort of excite the planet onto a very eccentric orbit. So it goes from wide and circular to wide and eccentric, and then due to tidal interactions with the star, the orbit then recircularizes, but at a much smaller orbit. So all these theories about migration basically came up from the discovery of these very sort of close-in planets.
And it turns out our solar system is sort of the odd man out, right? It's quite. I saw this paper back in the fall. I want to say it was in Nature Communications, but I'm not totally sure. But it was comparing the prevalence of different types of solar system, I don't know what you call them, exosystems. I'm not sure. Anyways, it showed that the most common type was this very homogeneous landscape of very similar planets, and I think they were maybe towards I think they were in the super Earth category, or maybe in the mini Neptune, but they were very homogeneous, and that these hodgepodge solar systems made up a small percentage, I want to say less than 10% of the total landscape. And I think that was maybe quite shocking, but also shows how studying our solar system is maybe not the best one to get a generalized picture of what's happening, something like that.
Yeah, no, I think that's definitely right in terms of that last point, that the solar system, at least of what we know of other exoplanet systems, is a rarity and odd one out. We haven't really seen anything like our solar system, perhaps yet. And yeah, you're exactly right that this sort of, especially from the Kepler mission and the Kepler Space Telescope, found lots of these sort of multi-planet systems where it was these planets that were all very similar. These, yeah, you say planets between the size of Earth and Neptune, these super Earths and sub Neptunes, of which even we just found just in general before thinking about how these systems come together, just this type of singular planet is the most common type of planet in the in the huge galaxy. Even and people have done occurrence rates, population studies, and have found that these planets between 1.5 and 3 sort of Earth radii are the most common planets, or some of the most common planets in the universe, and we just don't have a single planet like that in our solar system, which then just even makes us more of an outlier in some ways. And yeah, then you find these very compact multi-planet systems where you have 3 or 4 planets very similar to each other, all in a quite close orbit. Again, nothing like what we might see in the solar system. But I do think part of me is also thinking that sort of we haven't really found a solar system, but I think it's more we haven't found a solar system yet, because the current methods we have to find planets are very heavily biased towards finding planets that are close into their star. Sort of the main 2 methods are the transit method and the radial velocity method, the 2 I mentioned. So the transit method, you need the planet to actually pass in front of the star, which if you have a randomly aligned orientated orbit, it's much more likely to transit if the planet's closer in. And also if the planet takes sort of only a few days to orbit its star, you can observe the star for a few months and observe tens of orbits, tens of transits. But if the planet takes a year, you could observe it for 6 months, and even if the planet does transit, you might not see it at all.
And our gas giants take more than a year, right? They take a very long time.
Yes, yeah, and some of the gas giants in our solar system, take many years,
like tens of years. I think decades. Yeah.
So,
very long time.
What's in terms of stars that are close enough to be able to study these sorts of transits? What percentage of them are we watching on a regular enough basis to be able to see a transit that takes 5 years, 10 years? Like, is there what percentage of stars are continuously monitored in such a way that you can confidently say that we have characterized this to a degree that we're relatively certain that what we see is what is there?
Yes, right. So, I mean, actually, at the minute, currently, there's a telescope in space called the Transiting Exoplanet Survey Satellite, TESS. It's a NASA mission that launched, I think, nearly 5 years ago in the summer of 2018. And this is doing exactly that. It's continuously observing the sky, looking for these transiting exoplanets. And it observes it in a way that it will constantly observe sort of a strip of the sky that comes to, I want to say, roughly a few percent of the total coverage of the sky is observed at any one time. And then, but TESS has been sort of rotating around, and I think the total bits of the sky that have been observed by TESS for at least 27 days is nearly sort of 90% of the sky has been observed now by TESS. But again, as you say, the problem is to find these very long period planets. TESS isn't ideal for this because it only observes in short chunks and moves on. So a lot of the long period transiting planets that we know came from the Kepler mission, which picked a patch of the sky, stared at it for 4 years or a few years, and basically continuously. And if a planet transited, TESS had a very high precision and a very long coverage and found a lot of these long period planets. But again, these sort of, by the time you get out to a 5-year orbit, the probability that the planet transits is minuscule. It's much less than 1%, probably a few hundredths of a percent probability that the 5-year orbit planet will actually transit. So I think that's sort of the main reason why we've struggled so far to find these long period planets. We just need to get lucky with the right star.
Really quick, guys, we hope you're enjoying this conversation with Dr. Bryant. We depend on you for support. Our patrons are the lifeblood of this operation. We cannot do it without you. If you join our Patreon, you can participate in a weekly conversation where we get together and brainstorm what happens next. It's vital to what happens and making this a better and better program. If you've already done that, please continue to comment, share the podcast. It's the only way that it gets spread around. The YouTube algorithms are not helping us out. We are not radical enough in any direction. So tell us your ideas, talk to us, come join us on Discord, and participate, please. It's so meaningful to us.
So come say hi at patreon.com/demystifysci, and if you can't, that's totally fine. We appreciate that you're here, and we love hearing your ideas, so just drop us a line any way that you can. And in the meantime, enjoy the conversation with Dr. Bryant.
Well, Kepler was very good at finding the planets that were transiting because it only observed one patch of sky. The total numbers of stars it was studying was much less. TESS is observing many more stars, but for short periods of time. So it's much harder to find these long period planets.
And that's sort of a fascinating bigger paradigm in astronomy, which is that you're heavily biased towards the convenient things, the bright, the close by, the things that are really making stand out. Because you're looking at things that are so far away, right?
Can you make the case that that's not all of science, though?
It could be a general scientific issue. I mean, science is wonderful because it makes these very clear, certain statements based on what it can observe, but has a hard time with things that it can't observe. This is a general problem, I suppose.
I mean, there's a really lovely picture that I like, where it has sort of its arse impression of what the Milky Way galaxy would look like from sort of a top-down view. And then the position of the sun is labeled sort of out in one of the spiral arms of the galaxy. And then there's sort of a very small ring of yellow dots, very small ring of dots around the sun, with then a streak going off in one direction. And it's sort of a tiny fraction of the total volume of the galaxy has a point in it. And each one of those points are all the exoplanets we know. And so even though we have sort of these thousands of known exoplanets, that's only a tiny little fraction of just one galaxy that we've surveyed. And so, you're exactly right that we are still limited to focusing on stars in our neighborhood in the solar neighborhood of the galaxy, which is only one galaxy out of billions. And that streak going off being what Kepler observed, going sort of observed for longer and with a bigger telescope could look further away. But we are very limited in trying to study this sort of small patch of sky and make big extrapolations out to estimate overall populations.
And not just this small sky, but the ones that are close to the sun and so forth, right? I think it's so fascinating how many planets might be out there. You know, the concept of rogue planet made some headlines a few years ago, right? And I think there's obviously no way of directly detecting these planets that might not be attached to a star system, because all of our methods rely upon the star as the primary readout.
And periodicity.
Oh, yeah. So there's no pattern to it, right? If they're just floating around at the edge in between stars. And I just think that it's really inspiring to imagine how much is happening that we can't see yet, just because we don't have the tools, or our methods are relying upon those things that are the lowest hanging fruit right now.
So this is really a far out question, and if you tell me that it's absolutely absurd, I will take you at your word. But I've always wondered, so we have the galactic rotation problem, where the edges of the galaxy rotate faster than they should based off of how much observed mass is there.
Yeah.
But we also know that we can't see stuff that's dark unless it's in this kind of periodic orbit around something that is bright so that we can actually see it shift. And we know that there's these rogue planets that are drifting in between solar systems. We suspect. Yeah. Okay, we suspect. So is it possible that there's just this accumulation of kind of, you know how when you go to the beach, there's the line in the sand where it deposits all the things that aren't held onto something, and as the tide shifts, you can see where that line remains in the sand. Is that possible that that's what's happening inside of a galaxy, or is that just Is that too simple of an explanation for how complex the mathematics get?
I'm not sure I fully understood sort of the C method. What do you mean? So
I think
there's
So, like,
deposits of
basically
free
things.
floating planets around the
Yeah.
outside of a galaxy? Or?
Yeah, well, because there has to be pressure that's coming from the center of the galaxy, right? There's outward pressure. There's cosmic rays. I assume that there's the equivalent of a solar wind that operates on the galactic level.
Possibly. Yeah, I don't know too much about that, to be honest.
I think that if I might just interject,
please.
I think that the issue with the accumulation of a bunch of debris is that the length of time since the formation of the galaxy is not sufficient to accumulate that amount of cold matter. Particularly cold is the key. The cooling process is not within the constraints of the standard models of cosmology and galactic formation. I think that's what it comes down to.
But the question is basically that, like, is it possible that there's an accumulation of cold stuff that's not attached to anything at the edges of the galaxy that would account for the rotation problem?
I don't think so. I'm not sure. I mean, I think the question is where this sort of cold matter would come from more than anything. Because I think, you can get these free-floating planets, or at least it's been theorized that you can, but a planet, the way we understand a planet, it needs to form around a star and then be ejected to become free-floating. And I think there was some work recently, or my understanding is that, this process is quite rare, that you would get an ejection to begin with. And then also you have these stars and planets form in very dense regions of space where there's lots of stars all packed in together in a cluster that slowly drift apart. But when these planets would get ejected from a star, there would be tens, hundreds of other stars sort of nearby that would also have gravitational interactions, and it might get captured by another star, or as Michael was saying, it would take it a very, very long time to make it to the outskirts of a galaxy, and I think longer than the age of the galaxy or the age of the universe to get out there.
Yeah, because the estimates, I tried to research this to write a piece about it a few years ago, and the estimates were wildly varying. Estimates of the number of rogue planets. I'm sorry. The estimates of the numbers were outrageous. They varied from one potential rogue planet per every 4 solar systems to 100,000 per solar system. Like because you can't. These are untestable theories, right? And they depend upon different free parameters in everyone's model, and so there's very little certainty that can be made about that. Now, maybe someday we'll send a probe out past into the Oort cloud and find all these planets everywhere. But until then, it's hard to say anything about that. And that's the cool thing about this, though. Just like with the recent tests and Kepler missions, is when we do make these discoveries, the paradigms have to shift to account for them, because you just can't carry on otherwise.
But so I think I remember reading something about last year. I think that there's transits and rarity is roughly the main two methods, but there's one of the other methods is called microlensing that's been used to detect some planets. So this is based off the sort of idea of gravitational lensing. So if you have a background star, a bright background star, and then a sort of foreground star passes in front, due to sort of general relativity and sort of space bending, due to the gravitational pull of the foreground star, sort of the light from the background star is sort of lensed around it, and you get this brightening of the background star and a lens and sort of a ring forming. And so, I mean, this has been done, as sort of predicted by Einstein, has been done for stars. If you sort of monitoring, a few planets have been found like this. So if you stare at a star and then a foreground star sort of passes in front of it, the intensity, the brightness sort of spikes up massively. And I think how this works is if the foreground star has a planet, which also comes out of orbit, so it's next to the foreground star as it passes, you get sort of a second spike from the planet lensing the background star a little bit as well. And And there's been a few planets detected through this sort of microlensing method so far. And I think there's a space telescope planned. I think it's the Nancy Grace Roman telescope that's going to do this, but it might be a different one that's planning, I think, to go in space. And some of its time will be a microlensing search for planets. And I think it was predicted that if there is a sort of substantial population of these free floating planets, the telescope might be powerful enough to actually detect the lensing spike from just a free floating planet passing in front of a background star. And so potentially as I say, I think it's the Nancy Grace Roman telescope, but it might be a different one. I might be wrong, but I think it's that one. Once that flies into space, it could be that we might start being able to actually detect and put for the first time, some real constraints on the population of these free floating planets and actually figure out how many of them there actually are. So, yeah.
How many of these exosolar systems have ecliptics that are aligned with ours? In other words, you can only see a planet in one of these transit or lensing events if it's going directly between us and the star. Is the galaxy are they more or less aligned along similar planes, or is it rather random?
It's mostly random, I think, the orientation that you get. Yeah, the orientation of these systems is fairly random. I mean, we know just from the ray velocity method, we know there's lots of planets which we can see their pull on the star, but they don't transit. So they're obviously in orbits that are sort of inclined. And there's the old method that I think Gaia will hopefully be revealing the presence of a lot of planets with this over the next few years, is astrometry. So again, based on the motion of a star due to a planet in orbit, but the rate velocity is again more sensitive to planets that would be on a transit-like orbit. But if you were to rotate it 90 degrees, you're looking top down onto the planetary system, then you would see the actual motion of the star. You could sort of track its position in space as the planet orbits around it. And so through all these sort of various methods, we are finding lots of planetary systems as well where they are not on transit-like orbits. So I think it's the case that a lot of these systems are on randomly inclined orbits. But of course, again, when we're looking at these systems, we're not necessarily looking out along the ecliptic. So we could be pointing the telescope sort of away from the plane of the orbits of the solar system planets and find a system that transits. So sometimes having a exoplanetary system that's not inclined in the same way as a solar system is actually beneficial for finding these transits, because we can look up away from the sun, away from the other planets, and find these as well.
You mentioned something about the possibility of planets leaving their solar systems as being extremely rare. Why do people think that that's extremely rare? Did you see? I didn't have a chance to look up the authors, but there was a really interesting mathematical piece that was trying to model the stability of solar systems, and the group of mathematicians came down on the side of solar systems being actually rather unstable. Like the resonances would build up to the point that they became unstable quite frequently, actually. And there was a paper that came out, I think, last month that described observing a star eating a nearby, like a planet fell into the star. And if stars are swallowing planets, why do you think they wouldn't be able to lose the ones that didn't have the appropriate angular momentum?
Yeah, so I think, again, that's a very interesting question, a very interesting area. I think a lot of this, where you have these two planets, as you were talking about with the resonances, and you become unstable, I think my understanding of where this sort of instability then comes is you excite this large sort of eccentricity in the orbit, and then that can take the planets onto very close to the star. And I think my understanding is that often when you get these instabilities, as I haven't read that paper you're mentioning, but when you can get these instabilities in the planetary orbits, often that results in just the planets going on a collision course with their star, before they sort of acquire the necessary energy to sort of escape away from the star, away from its orbit or from its gravitational pull. So I think a lot in this scenario where you have multiple planets that are then sort of resonantly exciting each other, or you get orbit crossings, I think a lot of the time that results in the planets sort of crashing into their star as opposed to being ejected from the solar system.
So it's like it's easier to be eaten than it is to be flung away. It's more energetically favorable.
Yeah, I'm not sure, but yeah, I think it's definitely easier and probably more energetically favorable as well, or that in order to sort of excite the sort of large amount of energy you might need, you probably might end up having to be kicked into an orbit. I don't think another planet would be able to by itself excite enough energy for a planet to escape. Maybe it could in some scenarios, but I can sort of envision if potentially a planet could sort of go down, and it would have to, in order to build up the energy, it might have to orbit very close to the star to sort of build up this energy. And whether that could ever result in the planet sort of escaping, or at this point it's always bound, and no matter how far away from the star it goes on this orbit, it will always, in these scenarios, whether it would always eventually be pulled back. I think the ejections tend to be where, as I say, these stars are forming in these sort of dense environments where there's lots of other stars around. And if you have a planet forming around one star, then you could have a scenario where another star comes close to the orbit, and it's an interaction between this sort of passing star and the planet is what can sort of, through a new gravitational interaction, can what excite that sort of ejection of the planet from the system. But yeah, I think these are quite rare events. I think there was some work potentially also recently that showed these were quite rare events to happen. But again, we don't, as you were saying, we don't know how rare or common these could be until we can start looking for these free-floating planets.
Well, there is maybe a proxy way of looking, because if you assume that you have a collection of systems that you've been looking at since 1995, right? So at least some of them we've been looking at for decades now.
Yep.
And so you would be able to estimate the rate at which those orbits change and disappear. But I don't know, once something is discovered, how much time is spent going back and monitoring changes. Like, it feels like the goal of the field is to continue to find more, as opposed to be like, let's go back to the first one and see, is it still the same?
I think, that's a very good point in that, I mean, some of these missions like TESS are finding planets at such a rate that in order to sort of confirm these planets, you generally people want to, or you need to try and get some estimation of the mass through further observations, and there can just be an observational bottleneck where we just have too many planets to observe for the amount of telescopes available. And so, you're exactly right that the field at the minute is focused on, a lot of the field is focused on trying to find new planets. Or then there are missions now coming along, there are work to sort of go back and re-observe known systems, but that's more in terms of studying their atmosphere or trying to find out something new about them. Although there are recently, over the past few years, there have been talking about sort of the planet engulfment in the stars and things. There has been some work done on these very short period giant planets, where for some of them there has been detections of sort of the orbit actually changing, of the orbit shrinking and the period getting shorter over a time scale of 10, 15 years. The main planet for which this has been seen is a WASP-12b. So it's a giant Jupiter-sized planet. I think it's slightly larger than a Jupiter, around a sort of a star, and it has an orbital period of about a day. And if you people have sort of tracked the transit time, because you can obviously measure when the planet transits, and you can get a very precise timing of order of 5, 10, 15 seconds of when the planet passed in front of the star. And people have been monitoring this and other very short period giant planets over 5, 10 years. There's a small subset where this has been done. And for WASP-12, definitely so far, there's actually been observed each sort of subsequent transit you can see them arriving earlier and earlier. You can't see it for individual transits because per orbit sort of the change is so slight. But if you map it out over sort of a 10, 15-year baseline, you can actually see this decay in the orbit and and this change in the orbital period as the planet is spiraling in towards its star.
Mm. Yeah, these two, I just wanted to say the two gentlemen I was referring to are Marcel Gardia and Jacques Fehoz, who are they're mathematicians at the University of Barcelona. Right. And they were actually proposing a mechanism by which the orbital distance would increase. And it would happen over a matter of millions of years as opposed to billions of years, which is generally thought. Of course, this is a purely mathematical representation, but they were at least providing a mechanism for how that might happen.
Is that in Quanta?
This is a Quanta magazine. Yeah, I'll try to remember to put this in the description so people can follow up on it.
I mean, it strikes me that there is a huge disparity in the number of questions that people want to ask and the number of opportunities that you have to ask them. Because, like you said, telescope time, observation time, as far as I understand it, there's like a lottery in terms of what projects get approved. Is that the case?
Yeah, so for a lot of these telescopes, there's sort of a lottery, it's a proposal system where a lot of these telescopes, they're often sort of funded by sort of agencies, big bodies. So there's a bunch of telescopes in Chile at the European Southern Observatory, so ESO, which is this body which owns and operates all the telescopes, and also for some space telescopes like Hubble, JWST. A lot of these, to get time on them, you have to write and submit an observing proposal, which basically lays out the science you want to do, the questions you want to answer, why your science is the most important science to be done. And then panels sit down and review them and have to try and decide which ones get observing time. And I think the recent JWST proposal cycle was oversubscribed by a factor of 7. So there were sort of 7 times as much time was proposed for as was available to be observed. And so, you're right that there's a lot of science out there that people want to do, but it's just we're really limited by the availability of telescopes at the minute just to try and actually get this science done. I mean, there's a huge amount of very exciting science being done, but there's a lot more that people want to do.
We had a really, really cool conversation with Beatrice Villarreal. Do you know her? She runs the Vasco project, which is the vanishing century of stars.
Oh, okay.
So she did this really interesting...
Stellar objects.
Stellar objects, pardon me. She is very careful not to say that they are disappearing stars. She's like, we cannot prove that they're disappearing stars. But what she did is she took pictures from the Sloan Digital Sky Survey, or the Sloan Whole Sky Survey, I think it was, that was taken 50 years ago.
Yeah.
And then pictures that were taken in the last, 10 years or so, and compared the slides between 50 years ago and today, and she found hundreds of thousands of objects that were missing in between them. And they did some kind of process by which they narrowed it, and she was like, look, some of these are definitely, they could be weird things, because there's not a machine learning way that they can process the slides. It's hand done.
Right.
So you can imagine the absolute load of work that is. And so she's trying to turn it into a citizen science project where she's, recruiting people to sit around on their computers and do it. But it was just really interesting to me where she, I think, dealt with the limitation of telescope time by basically saying, okay, well, we have historical data sets and we have modern data sets, and so let's compare them and see what we discover. And she's found this kind of perplexing gap in the collection of objects. And it opens up all kinds of really interesting questions where I think that the James Webb is kind of tied to this, where there's been a lot of consternation over the fully formed high redshift galaxies.
Yes.
And our models for how solar systems develop and behave and change are fundamentally bounded by the age of the universe. Agree or disagree?
Yes. Agree.
And so if the age of the universe gets shifted because we're suddenly like, okay, well, maybe they couldn't have fully formed galaxies in the first 500 million years after the Big Bang, and we have to shift that timescale. What do you think could change in our paradigms of planetary formation and star formation and star evolution that right now seem fixed to the wall? But if you change this one fundamental parameter, that would be different.
So it's really interesting. I think in terms of planets, largely, sort of the exact age of the universe doesn't have a huge amount of bearing on what we think for planet formation, because of planet formation, we think most of it sort of stars form in a few million years, and we think a lot of the, at least formation of the planets takes place within 10 million years of the star being formed, and then a lot of the...
That's so fast.
Very fast. Very, very fast, yes. And then, yeah, there's been a lot of work. Actually, people initially were sort of, they came up with planetary formation theories, and then there was actually some work done across the past 10 years or so, actually trying to go, well, actually, these current theories, we couldn't form planets quickly enough. I think we knew based on sort of protoplanetary disk lifetimes that protoplanetary disks largely are dissipated, are gone by 10, 20 million years after the formation of the star. And so we know the planets need to form within that time. And these theories initially couldn't build up the planets fast enough. And then people came up with some very clever ways and some new ideas for how you could sort of accelerate the planet formation process through either you could sort of get these sort of pressure traps in protoplanetary disks. Like if you sort of if you started forming a planet, it could sort of carve out a gap in the disk, and then this can sort of trap, because in the protoplanetary disk, a lot of the building material is constantly streaming in towards the star, and so you're losing a lot of material. But if you can perform this pressure trap or build this trap or this gap, you can actually trap some of that material, and then it can still be there and available. And then you can get these other mechanisms as well to basically accelerate this planet formation process. But yeah, basically the things that we know these planets have to form within a few to 10 million years. And a lot of the migration and evolution processes take place within a billion years. So in fact, for a lot of these planetary systems and planet formation timescale, actually how old the universe is doesn't really have a huge amount of bearing on the planetary systems we're observing.
But there was, it reminds me of the geology in the 1800s, where people were initially very convinced that the Earth formed in a matter of thousands of years at first. And then as they began really coming up with new dating methods, this became untenable. And the idea shifted enormously. Another example would be the early Hubble work, Hubble's early work, where people were arguing over whether our galaxy was the extent of the universe or not. And they started finding these satellite nebula, and eventually they realized they were fully formed galaxies. And all of a sudden, the size of the universe exponentially increased all of a sudden. And I wonder if this exoplanetary science is also in these early days where our formation models are in some way subject to, massive extensions in the future as we come to understand things better.
Yeah, like to build on that a little bit, something that I've always thought is that we in science have a tendency of wanting to have a single explanation, where we're like, this is the model and this is the equation and this is how it works. Done. Let's move on to the next question. And to me, it seems in something as enormous as the universe, it seems absurd that there would be a single paradigm for how things form. Yeah,
no, definitely. Yeah.
And so I guess the question here is there space in astrophysics and planetary sciences for there to be a multitude of paths to the same objects, or is it still considered that there's not this ability for convergent evolution where you have multiple processes that lead you to a planet?
That's a very good point. And I definitely think that in something that you look at just even one patch of sky and you can find sort of 100 different planets or styles of planet, I think, you're exactly right that for people to think there could be sort of one single formation mechanism that perfectly fits all planets, I don't think that will be the case. I think there already are a couple of different formation mechanisms. So there's sort of core accretion, pebble accretion, which is sort of bottom up, where you have these solids and rocks and things in a protoplanetary disk that combine together to build a core, and then you can either stop there at a small rocky-like planet, or you can accrete gas and form a giant planet, or you can get sort of top down, so gravitational disk instability, where the disk directly fragments and you form a giant planet. And maybe these form sort of slightly different populations or stars of planets, but these populations overlap at the edges. And so I think we're really beginning to understand also the fact that based on most of our observations so far, we can know how heavy a planet is and what its diameter is. And then we're trying to make all these sort of predictions about what its core is made of and where it came from based on just these two measurements. And with JWST coming along and we're able to look in the atmospheres, we're sort of finding out that even, say, within Jupiter-sized planets, within 3 days of their star, there's actually could then be a huge range of what molecules do we see in these atmospheres? Do they have clouds? Do they not? How much carbon is there? And these are all telling us all sorts of things about, and could potentially tell us with JWST and with a European telescope, Ariel, that we'll be launching in 6 years, I think, hopefully as well, to try and study study the atmospheres of a large number of these sort of giant planets. And I think, we're seeing that, or at least my opinion is that these planets are so diverse, and every year there's this new class of planets that pop up that we're like, how did this planet form? Like there's a sort of subset of planets that's beginning to find a few more where you have a sort of giant planet on an orbit of less than 10 days, sort of 4 days, 5 days, 6 days. And then there's a sort of super Earth-sized planet between the giant planet and the star. And it's sort of the question of how did this form? How did you get this sort of giant planet to move all the way into the star, and yet you could still have a smaller planet within the orbit of this Jupiter-sized planet? And then again, that then brings in, okay, well then there must need to be some other form of evolution or formation mechanism to produce this type of planet. And I think it will be the case that, and again, we're just looking at a tiny small area of one galaxy. And I think you're right, there is a tendency to go, well, we have planets and we have planet formation, and we come up with a model that explains where these planets come from. But I think, as we find more and we learn more about individual systems, I wouldn't be surprised at all if we start seeing that a lot of these planet systems are very different from one another, and potentially there isn't an overarching theory that governs all planets, or maybe it is, but it's formed up of 10 possible pathways, and planets might go down some of 5 of them during their evolution, but other planets might do different ones. And
I think that evolution is another really interesting aspect that we haven't touched on, which is how some of these gassy planets are getting their atmospheres cooked off when they're close to the star, which is, of course, going to make them look very different later on than they would while they're spending time. And if they were to migrate after that, then, what happened? You can't look at the extant atmosphere and think that was how it formed.
Yeah. Oh, we had a really fascinating conversation on the podcast with, was it Don Petit, right?
The astronaut?
Yeah, so we had this NASA astronaut who is also, I think his background is chemical engineering, and he had an advisor during grad school who really liked like Feynman type back of the envelope riddles. And one of the things that they came across was that the pteranodon dinosaurs were too big to fly, given the wing loading body size graph. Like there's a I think it's Tanneke's Great Flight Diagram, and on Tanneke's Great Flight Diagram you basically have, I think that it's wing loading versus weight of the device, and everything has to fall in that line, even from Boeing 747s all the way down to mayflies. And these pteranodons are just way off the chart. And so his advisor was like, okay, well, let's figure out what it could have been. And one of the things that they came to was they were like, well, it's possible that the atmospheric composition of the Earth was the same, but there was just more atmosphere. And so they were able to fly under different conditions. And, you know, he went on to be an astronaut, so he didn't spend a tremendous amount of time pursuing this as, you know, trying to change the paradigm. But what was the paper that you found about the evolution of the many Neptune atmospheres, where they basically form cold and then move in to the inner part of the solar system?
Well, there's this really, maybe you can comment on this too. There's this interesting gap in the radii, right? So there's one size of planets, I think the super Earths, and then there's a valley where the next size of planets are these mini Neptunes, and they're not sure what happens to the ones in between, essentially. And so one idea was that they lose a lot of their atmosphere somehow and evolve into that. Of course, I think the more popular ideas are that there's collisions during the migrations that eliminate the mid-sized planets. But it's a very interesting paradox in planetary formation.
Oh, yeah, no, definitely. This radius valley that people start calling it. There's actually quite a few people at MSSL where I work who are focusing on this radius valley, trying to find new planets around it, trying to understand it better. And yeah, you're exactly right that we know it's there, and we have some theories of how it could possibly have got there. Yeah, you're right. There's this photoevaporation, which is that these planets come in close to the star, and then some of them have their sort of atmospheres subject to intense sort of UV irradiation, and it excites the excites the particles in the atmosphere, and basically strips the atmospheres away, and you end up with this sort of dichotomy of planets that have kept their atmosphere versus planets that haven't. Or there's some theory that some of these planets just form in a disk that doesn't have as much gas available when the planet's forming, and so it can't accrete an atmosphere to begin with. There's some other theories that actually we're sort of seeing two different sort of types of planets. Potentially there's sort of these planets that are more rocky in their core, and some planets where sort of the bulk of them is made up of sort of water ices and sort of icy material. And then these give these sort of two planets sort of very different densities. And it could be that you sort of have these sort of slightly different compositions of planets, which are giving a rise to some of this population. But again, yeah, you're exactly right. It's this thing where we're seeing this population begin to rise, and a lot of work's being put into trying to understand what could have caused it, and whether it is just the one mechanism, or whether, again, all these mechanisms are playing a role, more some than others for particular systems, to carve out this gap.
We had a conversation a long time ago now with Jibor Basri, who's at UC Berkeley, and he studies brown dwarfs.
Yes.
And I came away from that conversation with this feeling that there was a real difficulty of being able to evaluate the path of formation for star versus brown dwarf at some point. Like really, really low mass stars and really, really high mass brown dwarfs basically look the same.
Yeah.
And then it becomes a question of, okay, well, how many of the objects that we see that are verging on the size of a low mass sun are formed by the same process as the sun, but they just don't get all the way there? Like, is that possible?
Yeah, so again, these sort of brown dwarfs are a fascinating sort of class of object that sort of, it is, as well at this upper end, they're sort of there, but they almost bridge the gap between sort of planets and stars in some way. And yeah, I think it could be possible that if you form a star from a sort of cloud of gas, and if this initial gas cloud is small and not very massive, then you could begin to form what might hope to become a sun-like star. But if it just doesn't have enough mass, it might not be able to sort of fully form into a star. But then also sort of down at the other end of the brown dwarf spectrum, you have these very low mass brown dwarfs can look almost indistinguishable from a very high mass planet. So these brown dwarfs as well, they have a characteristic radius of about very similar to the radius of Jupiter. So you have these systems where you can be observing this planet, and based on just the transits alone, it could be a 1 Jupiter mass planet, or it could be a 20 Jupiter mass brown dwarf. And it's again, there's a lot of question going into, okay, where exactly is that shift from a planet to a brown dwarf? Often people use about 13 Jupiter masses as the cutoff between, if it's less mass than that, it's a planet. If it's more massive than that, it's a brown dwarf. But then again, that then comes into a sort of another question of, well, what distinguishes it? Is it just the mass, or do they form in slightly different ways? If it's a formation mechanism, could it be that you actually, again, have these two populations where the tails overlap, and so you can get some planets which have formed through a planetary formation mechanism that are actually more massive than something that may have formed through a stellar formation mechanism. And it's again this sort of area where almost the more objects we find and the more we learn about it, sort of the murkier it becomes and the harder it becomes to actually distinguish where one population ends and the other begins.
I mean, one aspect of it that one little thought experiment I play with all the time is that if you define the brown dwarf by the ability to fuse hydrogen, if you define a star by its ability to fuse hydrogen, the brown dwarfs can fuse some heavy hydrogen, I think, but not true fusion.
Yeah.
It seems like there must be, at some point there's a threshold where it gets enough atoms added to the ball that it's able to do the true fusion and be a star, but it's only one atom at the end of the day, which makes or breaks the deal. So it seems to me like there must be a class of objects which are right on the edge of becoming stars, and whether they gain or lose that atom is going to determine which road they go down. But maybe it's in some sense reversible too, like something might be a star and then it loses a little bit and now it's a brown dwarf. And I wonder if there's this flickering, just to sort of play off the Vasco project as well. I wonder if it's possible for a star to an object to sit right on that boundary level where it could go both ways or spend some time as both even.
Well, I think about that in context of the super far in gassy planets, the ones that have, let's say you have a giant 20 Jupiter diameter super gas giant.
20 Jupiter mass.
20 Jupiter mass, and it is super close into the sun. It's getting just blasted by the furnace of the sun, so it has to be losing a tremendous amount of atmosphere. Does that, if it survives, then change into a regular Jupiter? How long does that take? Like, I remember one time calculating for how long it would take for the sun to burn off that amount of atmosphere off of Jupiter if it was close in, and I think that it was an order of magnitude older than the universe, but
really?
But that was for a sun, and for our sun, and our sun is relatively small relative to stars in general,
well,
and so
it's pretty garden variety.
Is it?
Most of the stars are pretty small, actually. Yeah,
really?
Most of them are really small.
I did not
like
know
90%
that.
are M-class little dwarfy things.
Yeah, and also it's like 75-80%.
75.
Less massive than the sun. But that sort of numbers of stars, I think, also comes away from potentially it's again that it's sort of, to some extent, you can maybe think about it, it's easier to have two small clouds and one big cloud sometimes, and you form these smaller planets. But I think it's more to do with the fact that a much bigger star has a much shorter life. So these sort of, if you have these sort of, a lot of these M dwarfs are very old, and they've been around for a very long time, but they last this long because they're not as big, so they don't burn through the fuel in their core as quickly. But these stars that are 2-3 times the mass of the sun can burn through all their material in comparably a very short space of time. And so then it's also the case of, okay, maybe they might be, if they did have a planet around them, maybe they might be sort of affecting the atmosphere much more quickly, but then they also have less time in which to affect the atmosphere before the star becomes a supergiant or explodes in a supernova, and then there's no planet really to worry about anyway, most of the time.
Unless it leaves.
Unless it leaves.
Yeah.
Yeah.
Yeah, go ahead.
So I was just thinking, in terms of the sort of the mass loss timescales for these planets, even if they're very close, I think they can be very long. I think it's sort of early on, when the planets themselves can still be quite hot. So planets themselves are quite hot when they form, and they cool down and contract a bit over time as well. And I think young stars tend to also be more active. So they have sort of more sort of outbursts of quite energetic UV radiation. You get a lot of this sort of quite energetic outbursts. And so I think a lot of the sort of atmospheric erosion actually takes place during sort of the first few million years of a planet's sort of evolution, or few tens of billions of years, as it comes into the again, I'm thinking back, I think sort of formation takes place about 10 million years, then it's only the next sort of few tens up to less than or few hundreds of millions of years after that you actually get this sort of photoevaporation taking place. It's very early on when the planet forms, the majority of it. So once the time that sort of a star becomes 1 billion years old, most sort of the planets cool down, and most of that mass loss is actually stopped. And there can still be sometimes some going on, like we've seen in some smaller planets, sort of more sort of Neptune style planets. They've actually been observed in wavelengths where we can see that they have sort of tails of helium evaporating off them. We can actually see some of these planets still evaporating, which is always very cool to see. So this does still take place, and we have observed it. But I think in terms of the giant planets, most of the time they don't tend to change their atmosphere too much once they sort of settle onto their sort of main lifetime.
I think we're thinking more about the Neptunes evolving. I mean, one thing that's always troubled me since I got into astronomy was just how the rocky planets, they're so troubling, because they're so, like, this is the most dense object in the solar system that we're sitting on right now, right? And the idea that,
like, why isn't that in the sun?
Yeah, why it's not in the sun? Why isn't all of the most dense stuff in the center of the gravitational system is just really, really bothered me. And I know that there's some different ways around that, of course. And I'm sure a lot of the heavy stuff did get sucked into the sun originally. But it's very perplexing to imagine something accreting that's so dense and isn't in the center of the solar system.
Yeah. Well, I think a lot of it comes, how a lot of this material sort of is able to stay out and form a planet, is that when the star forms from the cloud, the gas cloud initially, everything's rotating. And so everything, even when the star forms, it's rotating and the disk is rotating. And so all this sort of dense rocky material that sort of forms into that initial protoplanetary disk has its own orbital motion. Then actually, in order for it to come in, it's not just a case of it would fall straight in, is actually sort of spinning and is slightly, I think that makes it slightly resistant to falling straight onto the star. And then if you can form these planets before you lose that material, as I say, during the formation process, a lot of the material is drifting in towards the star and is being accreted by the star and is being lost. But some of the material that can actually form into a sort of large sort of planetary sized body and sort of get itself into a sort of continue on an orbit before most of that disk sort of dissipates, then it can actually sort of sit in a very stable orbit and won't be sort of accreted on. Or I think even, is the Earth's orbit changing? I can't remember. But yeah, I think even if these orbits do change, they happen very, very slowly, especially once you get as far out as the Earth is. And so, yeah, these planets can then form and sit on these nice stable orbits. Although, as you say, a lot of the material that would go into forming something like the Earth is lost into the star during the formation process.
One thing that soothed my mind a little bit was I originally was envisioning the model as these huge particulate gassy nebula that are collapsing, but it occurred to me that there must be a fair amount of already accreted material flying around, because if you look at, we're told that let's say, the rock that our planet is primarily made out of, the silicates and iron and nickel, that they come from exploded stars. And there's a very beautiful image of at least a supernova that they've been tracking for a while. And it has almost these blobs of radioactive nickel and iron that are seen in the ring around the thing, right? And it's like, there must be just huge chunks of rock in place already before the solar system proper forms. Like, a lot of those things seem like they could be starting components in the first place.
Like, are you suggesting that you have a star that is large enough to have those things inside of it, and then it goes supernova, and instead of atomizing everything, you have the equivalent of cosmic spherules?
Well, even if
forming?
it's atomized, there's just huge. I wish we could pull up this picture. These huge blobs of radioactive iron and nickel, easily planet-sized, and even if they're atomized, they might congeal. They're very hot, and so you might have pretty large starting blocks, like planetary-sized starting blocks from those supernova. I don't know. It just occurs to me.
So actually, this I think ties into a different conversation that you and I were having, which is about the 21 centimeter line. So hydrogen has this 21 centimeter line. And the explanation that's given is that it is this spin flip of the electron that's causing it. But it's a really, really, really big wavelength. And it's hard for me, and it's never been observed, as far as I can tell, on Earth. And so it feels like, to me, what it is a large structure that is moving.
Like a lot of hydrogens.
Like a lot of hydrogens together have to move in order to produce that. Because if you think about the way that like a radio antenna works, you have a bunch of atoms that are arranged in a specific way that when they all move together, you get this macro scale wave that's generated and then passed away from the antenna. And so I wonder if there aren't large structures that are inherent in this mixing after supernova, where things get blown apart and some stuff gets atomized, but then there's a lot of stuff that kind of remains clustered.
Like if the molecular clouds have some structure to them inherently anyways. And
I remember, God, do you remember when we were talking, was it Batigan that we were talking to? And we asked him about the elemental composition of these clouds, and he was like, I just look at hydrogen. I don't worry about that other stuff.
Certainly the most of it is hydrogen and small, but it's acknowledged that there's lots of molecules in these, they're called molecular clouds, right? And so I just wonder, because there isn't a lot of discussion of the big, meaty, rocky, metallic pieces that go into the construction of a solar system. And if you have some pretty large chunks, then you kind of get past the pebble boulder problem more easily.
Can you wrap this into a question?
I don't know. I just wanted to put it in front of you. It's just something that I've been thinking about a lot.
It's very interesting, and I don't know. I haven't sort of seen this supernova image that you're talking about, or
I'll send it to you after we get off
about this. But no, I mean, I'm not too sure how big something could be once it's sort of experienced a supernova and this sort of huge explosion. I think most of the stuff that's sort of within a star tends to also be sort of very highly ionized, because it's very hot and very pressurized. A lot of this stuff forms down near the core as well. I
think it could be. I think it is ionized for sure, but it's in such proximity, they form blobs for some reason. They're these little nodules in the ring of, and if you think about the composition of an end stage star at supernova point, if you just look at the layered structure of it, it's very similar in composition to the structure of the Earth or a rocky planet. Actually, it's like the same stuff. So I'm thinking, well, if you have all that same stuff already in one place at one time, maybe it can get together later, or it finds itself, cooling in the vicinity, and you have more starting blocks to form some of these rocky planets because they're very strange. The gassy ones make perfect sense to me as part of the accretion. I mean, not perfect sense, but I can see it at least. But the rocky ones, I just have a really hard time imagining.
Isn't there like a pebble boulder problem of some kind?
Yeah. Is this in terms of sort of planet formation and things?
Accretion.
Yeah, so like the accretion model can get to pebbles, but then it can't get to boulders because the pebbles, when they hit each other, would just crack apart.
Possibly. I'm not too familiar with that, to be honest. But yeah, I know there's people have been now talking about pebbles and planetesimals in sort of accretion and formation mechanisms. I'm not too sure about this pebble boulder problem personally, though.
So we go out into the woods, and we just one day a week we get to go out into the woods, and we spend our time thinking about this kind of stuff. And Shilo's been teaching this astronomy course, and so these are just, you are on the receiving end of every single open question that we have about this that I don't think that anybody has the answers to. So I wouldn't necessarily feel too bad, because this is the process of us just being like, well, how do you get such a diversity of forms? Because I'm a biologist by trade, right? So I studied microbes, and I spend a lot of time thinking about the origin of life, and I spend a lot of time thinking about chemistry, and I spend a lot of time thinking about the way that you go from, just molecules bumping into each other towards something that is no longer just molecules. It now has will, and it has desire, and it has agency. And then it's not just bacteria, but it's also cats and elephants and birds and whatever. And so there's just this form that we have where we look at evolution, and it starts with something that's called the last universal common ancestor, right? It's called Luca. And so you trace all the way back, and you get to you see these trees of life, right? So you get down to the very, very bottom, and there's just this seed that starts everything. And you're like, that's a very neat, clean, and convenient picture. But there's recently been the realization that, look, there is the last universal common, or the first universal common ancestor, but there's also this massive diversity of stuff that kind of seethes underneath that neat picture that had to come together to create the neat starting point for the story that we tell. And with biology, and I think like with astronomy, there's the same mindset of, well, it was different long ago. And so we tell the story of how it was long ago that is particular to that time and place. And it's not happening right now, and it's very different right now. And so what we see right now is not reflective of how it once used to be. And I have this sneaking suspicion about something like the origin of life, where that's not totally accurate. Because let's
just come out right with it. I mean, the idea is essentially that perhaps life is happening all of the time. It's just happening and getting gobbled up, or it's happening deep under the crust, or in these vents, or somewhere where we wouldn't see it happening. And so life wasn't this event in the past. It's actually something that's continually happening, but we just don't see it, much like these planets that might be far away from their stars or something. We just can't build it into our model because it's not empirically validated.
And there's like all this stuff like viruses. We can't fold viruses into the picture of where they come from or what they do. There's also, you go out and you look at the DNA that's in the environment, and there's just tons that doesn't belong to anything. It doesn't look like anything that we know of. It doesn't fit together into pieces where you can be like, this is an organism. And so there's all this stuff that we look at where we're like, God, that's weird. Let's just not think about it. And I wonder if that's also kind of the case in astronomy as well, a little bit, where we're like, look, this is a picture, this is a frame that holds, we're fine with this, let's just operate in this. And then there's somebody who's in the back room when it's quiet, and they're like, there's a lot of weird stuff out there.
And maybe we can tie it. Yeah, go ahead.
Oh, yeah, I was just going to comment. Yeah, absolutely. I think there's all of basically exoplanets and astronomy is just, we had some theories of how planets formed and evolved from the solar system, and then we started finding, as I was saying earlier, sort of every exoplanet discovery we make more or less is just, this is something new that we haven't seen before, this is something new we didn't expect before. And then there's so much of finding these weird systems or these very strange systems, and then initially trying to sort of piece them into sort of the existing theories and the existing frameworks of, or maybe if we tweak this parameter a little bit, we can form these systems in these, or if we sort of assume that you can sort of form these pebbles together and these pebbles build and form up, then maybe you do get these systems forming. And as we find more and the theories develop, then some of these answers become more clear and more concrete, and they begin to match up better. But every time we look somewhere new, we find a lot of planets that we knew were there, and then we also find some planets that are very strange, and we're very confused as to how these came, and we can try and patch them into the existing frameworks, but sometimes we just need to then come up with a new framework to explain where these planets came from.
And how much of that has played out in your own mind in making this discovery about these planets that don't seem to fit with the stars that they're assigned to? I mean, obviously I read your paper. It's very observational, very technical.
Mm-hmm.
You spend almost all of the effort trying to convince the reader that this is a valid observation. Essentially, there's not much time for theorizing about where this planet came from.
Yeah.
Do you secretly spend time theorizing in your mind about the story of these bizarre planets in a way that you might not be able to necessarily construct a peer-reviewed article about?
Absolutely.
Yeah.
No, the paper is a lot of, we were looking for these sort of this population, looking for these planets in more of a statistical overview, trying to view the population. And then, I was having to spend a lot of the paper, a lot of the methods and the efforts was trying to rule out ways that these could not be real, because, a lot of people expected them to not be real. So we needed to try and cover as many bases as we could with the data we had available to try and rule out as many possible scenarios for these not being planets as we could. And I mean, that's half of finding planets, is convincing yourself that it's not one of the many non-planet scenarios that can give you the same signal. And then while I was then, I was writing it up and I was chatting a little bit with some people about, well, how could we form these planets? They don't fit perfectly well into the paradigms. And then, I was secretly thinking about, well, maybe this could be what it's coming from. And I think
Can you share some of your secrets?
Yeah, I can share some.
Off the record, just late night.
Not peer reviewed.
You're very tired. You're tired. It's the end of the day. You didn't know what you were saying.
So there's two main hurdles to forming these planets. The first is sort of the amount of material that's available in the protoplanetary disks, and then there's also a slight problem as well in that if you have a lower mass star, the planetary cores actually form more slowly. And so people thought, well, even if you could form it, the disk would be gone by the time, and your planet would still be too small to be a giant. Although in that second one, there's been some observations over the past few years of what people have started terming these Peter Pan disks, which are these sort of seem to be these very old, very long-lived gas-rich disks. So whereas I was saying most disks, we expect them to only last for 10 million years, I think there was an observation of a Peter Pan disk. So this disk that's still there, still rich in gas around the star, that's nearly 50 million years old, 55 million years old. And I think there's actually a lot of these disks have also been observed around these sort of 0.3, 0.4 solar mass stars. And so one of my theories is that potentially it's these sort of extreme long-lived disks that sort of persist for much longer than other protoplanetary disks, and so therefore potentially have a slightly different environment, could be where these sort of very rare planets, these planets with these small stars, maybe this is at least one of the places where they're forming, and how you're being able to build up enough of this planet and this core and accrete the gas onto the planet. And perhaps the formation does happen much slowly as people thought it would, but you have these environments where you can have that much slower formation and still form that giant planet. And potentially there's a link there into how these planets could be forming.
How much material is in the protoplanetary disk versus the star itself? Because we're talking about gas giants that are 40% of the size of the star?
Yeah, so again, these giant planets, they can be sort of, the ones we're looking at, they're about, in terms of radius, they're about 25%, I think, the radius, because you have a 0.4, if you have a 0.4 solar mass star, it's about 0.4 solar radii as well, roughly. And I think one Jupiter radius is about 10% of the radius of the sun. So you have about 0.1 solar radii for one Jupiter radius. But then I can't remember the numbers off my head, but I think the mass of the planet is actually much, much less than that same weighting. Like the mass ratio is still sort of closer to the order of sort of a few percent, these planets still, but the radii are much similar. But I think even, again, this is sort of, again, that limiting factor is sort of how well we understand protoplanetary disks. And there's been some sort of thoughts and some observations that seem to put a upper limit of about 10%. The mass of the star is the mass of the disk. And it's sort of believed that once you go above this, and it's sort of believed that this is roughly a cutoff for the size of these disks. But then even then, because of these sort of streaming effects and all the material being lost, people then think also, well, maybe only about 10% of the disk mass can actually go into forming a planet. So then you're left in a scenario where you, based on current observations of disks and current understanding of how planet formation works, people might argue, you might think that only maybe you could form a planet that's sort of maybe only 1% of the mass of the central star. I think I've got that right. So there's sort of this levels that people think these, and if you get a protoplanetary disk that gets much more massive than that, then it sort of becomes unstable very quickly. And so there's sort of, there's this sort of, that's basically, the theories of how big your protoplanetary disk can be, how much material you can have to form the star, to form the planet.
What would it take for you to be able to publish a theory like that, a peer-reviewed theory? What would you have to, could you do it? Would you have to collaborate with people who work on these disks specifically? Because I ran into this same problem. I'm publishing a paper too right now, and there's so many amazing conclusions that fall out of the work, and I just wanted to cram them all into there, like, oh my God, this can revolutionize the way we think about all of these different systems, because it's a very fundamental mathematical material science paper, but the implications are enormous. And my advisor was kind of like, well, that's not our job, like somebody else will have to follow that up and do all of the experiments to convince people that these possibilities actually play out in nature. And I'm always curious what that next level looks like, from taking some extraordinary observation about nature to proposing a theory that people will actually entertain about it, because just saying something doesn't seem to get you very far.
Yeah, no, you're exactly right. And I think if it was to try and lead this to a peer review paper, I'd have to, I probably couldn't do it all myself. I need to find someone who sort of understands the disks better and understands sort of the maths behind the formation better. And then we probably have to sit down and try and run some sort of, people run a lot of simulations where you basically try and build planets within sort of this simulation and see, okay, if we did turn up the disk lifetime, could we form this planet? And I actually have been, since the paper came out and sort of just before it, I've been talking with some people who work in a sort of in a different university, but one nearby, who they do a lot of work on sort of simulating these planet formation and trying to estimate what you could do, and then talking about they might sort of go away and basically take their existing framework, but sort of play with the parameters and, like, say, turn one dial up to a sort of an extreme value and then see if they could form these systems. And basically what the next step then is just, trying to go more to the theory and sort of the math side of it and just play around with the physics and with the parameters and with the how much stuff do you have in your disk to begin with, how long did your disk last, and then just try and see in what scenarios would these systems form.
Are there any scenarios in which we see the formation of planets in the absence of protoplanetary disks? Or is that because it seems like it would be easiest to see the formation of planets when you have a protoplanetary disk, because you have a disk, you have the clearing of the sweep, and then you can extrapolate that the sweep is the planet and it's forming, and it's obviously these things are related. But is it if there were planets that were being formed not in protoplanetary disks, would we be able to tell, or is the absence because we can tell and we know that it's not happening?
I think, that's very interesting. I think it's mostly that we don't expect planets to form not within a disk. We expect planets to always form from a disk, and as you say, the disk makes it much easier to find it. And I think potentially the fact that we always expect planets to form from a disk means we don't have an idea of what to look for a planet that wasn't forming in a disk. A lot of this work is sort of, we come up with a theory of what we expect and we go out and try and find it. And so I feel like if there was a way in which planets could form, but not in a disk, I think we'd first need to have some theoretical idea of what that would look like, before we could go and find it, or before we could even understand what it was if we saw it. I think actually sort of reminds me of the thing that although we found the first planet around a sun-like star was in 1995, actually some of the first observational evidence that planets existed outside the solar system was obtained, I think, in the 1910s, sort of many years before, and it was actually the observation of a polluted white dwarf. So these white dwarfs are sort of what the sun will eventually become in a few billion years. These are very small, very compact stars. And the settling timescales within these stars are so quick. So any sort of like rocky material that falls onto the envelope of a star within a few sort of tens of years is all the way down into the core. So if you actually observe a white dwarf, that you can see and observe this sort of rocky material in the envelope of the white dwarf, that means it's constantly accreting and absorbing this material, often from sort of a broken up planet that used to be in orbit around the star, that then through the star's evolution got broken up, got torn apart, and is now just a sort of set of sort of debris orbiting around the star. And we now understand, having found these planets and connect the dots, we now understand that if we see a polluted white dwarf, it's likely that there was a planet once around that star. Although when the polluted white dwarf was observed back in the early 20th century, sort of there wasn't that knowledge of planets around other stars to then connect those dots. So that's sort of although I think that most people, or at least currently, are fairly confident that planets form within disks. I think even if a planet did form or could form not in a disk, I think before we could be confident that we'd seen that, we'd need an idea of what we were looking at.
Can you really quickly clarify what a polluted white dwarf is?
Yeah, so a white dwarf is it's what sort of stars like the sun become at the end of their lifetime. When the star will expand, it will become a red giant, and then it will sort of blow off its outer layers, and it will contract, and what will left over will be a very hot, very dense, very compact star that's called a white dwarf. And a polluted white dwarf means that if you look at the spectrum, so if you look at the sort of how the brightness of this white dwarf changes with wavelength, you see lots of absorption lines in the spectrum of the white dwarf, basically showing that in the outer layers of the white dwarf, there's lots of sort of metals and rocky material and carbon and things within the outer layers. So that's what the pollution is.
And so it's thought that the pollution is sourced from planets that were destroyed in the process of shedding those layers.
So I think that's right, because it's believed that the sort of settling timescales. So it believes that if material falls into the or if there is material in the outer layer of a white dwarf, within only a very short period of time, that material actually sinks down into the core, and then you can't see it anymore in these methods. So in order for us to be able to see it, there sort of needs to be a continual source of this material onto the outside of the white dwarf. And it's believed that this continual source of material is the sort of leftover debris from a planet that was once in orbit, say around the star when it was like the sun on the main sequence. And then as the white dwarf, as a star evolves off the main sequence, it expands, it becomes a red giant, and it can sort of engulf the planet, and it can contract away, and you can be basically left with the planet but also as the star increases, sort of the tidal interactions increase as well, and through the evolution of the star, you can basically break up the planet, and the planet can then sort of become this disk of sort of basically rocks and rocky material orbiting the white dwarf that's then accreted onto it.
And how common is this? Like, what percentage of white dwarfs or polluted white dwarfs do you figure? I don't know why I'm so curious about this, but this feels somehow significant.
Yeah, I'm not too sure, to be honest, on the exact numbers.
Sure.
But I think it's fairly common, but I'm not too sure.
Fascinating. Okay.
I mean, one thing that strikes me is if there was to be an alternative planet formation mechanism, that the candidate would be something close to brown dwarf formation. I mean, that's the obvious mechanism that's already established, is sort of the failed star situation, which we touched on earlier.
There's the failed star situation, and there's also, like, let's say that Villarreal's work of vanishing astronomical objects, let's say that some fraction are actually stars that are going out. Some small fraction, but some fraction. Wouldn't that suggest that there is a downward...
Well, they have a name for this, right? There's this, after the white dwarf phase, eventually some of these white dwarfs will not be big enough to continue collapsing, and they will turn into black dwarfs. But this takes, I think, trillions of years by the theoretical accounts. So the timescales are just not accessible.
And so this brings me back to the point where it's like, if the age of the universe changes, and it turns out that stars can go out.
Suspend your disbelief.
I know, suspend the disbelief, right? So, like, let's say that it's possible that we're an order of magnitude off on the age of the universe.
Right.
Right, because all of these things are kind of cobbled together in this way that you look at the age of the universe and you're like, well, there's like 3 pieces that are important for judging the age of the universe, which is like redshift, cosmic microwave background, and like hydrogen ratios, right? What were you going to say?
Yeah, isotopic abundance.
Isotopic abundance. Okay, so like let's say that those can shift in a way where we discover something that we're like, that's actually older. Like, it doesn't seem like it would be that catastrophic of a shift. Like, okay, so we were wrong. Like, we thought that the universe was the Milky Way at some point. We're wrong. Like, that happens. Okay, so let's say it does. Then I can imagine it having an impact because we don't see a lot of supernovas.
In our galaxy.
And so if the path to death is big explosion and we don't see a lot of those, does that suggest that there's another path out of starness? If the timescales are long enough?
If the timescales are long enough, then potentially you could have a thing where if you turn the timescales up by a long way and these white dwarfs could potentially become these black dwarfs, then maybe you could see these sort of stars eventually going out. Although, I think the white dwarfs, they're more held up by electrons or degeneracy pressure more than fusion. So I'm not too sure on exactly how they end up going out. Maybe it does take a very long time. Maybe you could do it. Part of me is sort of thinking whether some of these vanishing stellar objects were in fact supernova, where in the initial, because often how we find a supernova sometimes is there's nothing there, then something appears, because the supernova are a lot brighter than what the star was. So whether they could just be the first time we observed that patch of sky, the supernova was already going off, And so we didn't realize that there was something new there. We just saw when the supernova died away and you were left with sort of a neutron star or something that's very faint. We then couldn't see anything there anymore. And maybe maybe sort of there are lots of supernova, or maybe more than we think, but we just haven't looked there before to realize that we couldn't see anything there before the supernova went off.
Yeah, and I think Beatrice is very careful in that paper that she is only left with a handful of objects that don't make sense. And I think some of them she does try to explain. There are also stars which appear all of a sudden. Yeah. And she's very careful not to call them stars. They're stellar, like quasi-stellar objects or something like that. But of course, and the timescales Anastasia is talking about are extraordinary. I think that it's actually more like 6 orders of magnitude for the length of the universe necessary to generate a population of brown dwarfs that could then serve as fodder for planets in the future.
So you're saying it's possible?
I mean, no cosmologist on Earth would agree, but I do think that it's intriguing because, I think that it's intriguing mainly because civilizations since long before modern science have been convinced of some sort of Big Bang. It's a very old idea. It predates modern science, and if we look at how our ideology has shaped our early science that we've walked back on, particularly with geology and the formation of the Earth, in
both directions. Hold on, let me add something to that. In both directions, right? Because if you look at geology, we have biblical catastrophism, and then we have uniformitarianism, and then we come back to, oh, holy shit, we probably do have regular catastrophes. But it's this pendulum swing between being like, God created the Earth out of chaos, to there has never been chaos, it has always looked exactly like this, and we live in a perfectly stable universe, to a gradual realization of like, perhaps we overdid it. Like, perhaps it's a little bit more nuanced than...
It just seems like there's a lot of bias loading the idea that there had to have been a creation event, and that we need to fit the observations from the sky to the creation event.
This is heretical.
I know. I don't. I'm just saying we should keep an open mind about our own biases in this situation, And if for some remarkable reason people decided to entertain other ideas, actually the steady state theories were entertained in the 70s and 80s, and ultimately Hoyle lost that battle. And maybe his model was wrong, but there, if some model emerged in the future that prolonged the duration, then we'll be looking at very different paradigms, not only in planetary formation, but in stellar evolution and everything, really, I think.
Yeah, I guess what I would ask at this point is, how are people reacting to the James Webb data? Do you see that is there like I see a lot of stuff in the press where there's, it feels like a deep attempt to reassure everybody that everything's okay. Where they're like, nothing is going to change, the James Webb data is fine, everything is fine. And then I wonder how it is inside the halls of astrophysics right now.
So at least sort of for my interaction with James Webb is sort of the more of the exoplanet side of it, where we're just more blown away at how good the data is more than anything else.
It's nice compartmentalization where you're like, maybe it changes the age, but it's like, it's the planets.
I think there was that. Well, I haven't kept up too much with this sort of initial that came out where people were, as you mentioned earlier, these very, very high redshift galaxies. Although then I think some people went back to it and maybe they hadn't accounted for everything in the observations properly, and maybe some of these galaxies weren't as high redshift as initially they were thought. But I think, so I'm not quite sure on that one, but I think in terms of the sort of exoplanet side of it, it's more just there's sort of less catastrophizing and more just excitement at how good the data is and what we're finding and what we could find.
Well, it's very difficult to find a cosmologist that is willing to think beyond, right? Because you're working inside of a whole structure that's over many lifetimes and many people, and there's a whole community. It's very difficult to get imaginative reconceptions from people that are working so close to those problems. So we like to put it in front of all of the astronomers and And I don't know. I mean, of course, like so much of this is just what could be, and we don't know. And of course, science is this really wonderful process of updating your priors and updating your conception of nature as you learn more about it. And unfortunately, sometimes people have a tendency to think that whatever the state of the art is the final answer. And, this trust the science stuff is a bit of a disaster because, of course, science is a process by which you're continually learning more. And so people get really locked into thinking that whatever the evidence says right now is the final answer. But that's not quite how it works.
Yeah, no, it's funny. I was thinking, I was at a meeting yesterday, and there was a sort of a theorist there, climate theorist, who works in the UK, and he was sort of saying something which I found quite funny. He was basically saying that, so he's a modeler, and he was saying, yes, all models are wrong. And sort of if a model fits the data very well, he then immediately gets worried because he knows that he knows that there must be some physics that's not in the model, either because the model can't be complex enough or we don't understand the physics yet. And I think he was saying part of what sort of is exciting for him and interesting for him is more just not being able to fit a model to every data, but seeing where the models can't fit the data, because then that reveals the new physics and something new that's going on that we haven't thought about yet and haven't considered yet. And that's then where you get those opportunities to learn the new physics and learn the new science and adapt the models, and build and then go again.
I like this guy. I think that's really exciting too. That's what I try to do, with my students as well, is spend most of the lecture on the problems, the things that we don't know. And it's difficult to balance that with this. I want them to also take away that it's not like we don't know anything, right? We have models, and I think that the concept of boundary conditions is really important too, because if you try to make a theory about everything all at once, you can't do it. But if you constrain your idea to some narrow circumstances, then you can say, okay, within this context, this makes sense. And people can be like, okay, yeah. But when you start to just broaden these sweeping generalizations, then we can get locked into one way of thinking and we miss all the fun little intricacies that emerge from the problems with the model, which is, like you said, where all of the really exciting discovery happens. Yeah. That's what the students need to go out and chase down in their lifetimes, essentially.
Yeah.
I really feel like there has been, over the course of the last few decades, there's been this kind of constriction in how imaginative it's possible to be in the sciences. Like, you go back, and we watched Cosmos recently, the Carl Sagan show.
Yeah.
It's crazy in some places. Like, the episode where he's talking about the aliens in Jupiter and the possibilities that are there, and he's a well-respected astrophysicist, and it's impossible for me to imagine the equivalent astrophysicist today feeling so free and open to make the same sorts of claims. Like, the most that I can maybe draw parallels to is, do you know Avi Loeb?
Yeah.
Remember the object that came through the solar system recently, the Oumuamua, and he was like, it's an extraterrestrial object. He got trounced. People were so mad at him, and they're treating him like he's just totally out of line for saying such things. There was a very tense SETI meeting where he got, he was told off. And I get this feeling that we've lost a certain amount of just wonder and possibility that has come down to the fact that there needs to be a respectability to science, where there are lines along which we pass, and these are the stories that we tell, and there are people that are outside the gates, the barbarians in the hinterlands, that are trying to tell you that, it's all electric universe, or it's all intelligent design, or it's all a simulation, or whatever else. Yeah. And so you have this very narrow rut in which you're like, these are the ideas that we will entertain because there's crazy people out there and we have to differentiate ourselves from them. And I wonder if that's something that you experience as someone who is still young in the field. And, Darwin had to sit on his ideas until his deathbed. he worked on his theory about what the origin of species looked like, basically until he died. And
Copernicus too.
Yeah, this is a long history of people holding onto their theories because there's an edifice around them that says that they can't possibly publish them and maintain the respect of their peers. And I wonder if that's something that you run into, or you feel like that's not really a thing, or a thing sometimes and not other times.
I think it's an interesting point you raise. I think there's definitely sort of within the sort of the peer review side and the publishing sort of, there's very much going towards nowadays we have such good instruments, we can learn more things and we can rule out a lot of these sort of weird and wonderful theories that we might like to think about sort of by ourselves in our offices. But I think we also can, to some extent, run into this. I always think it's quite tricky going when sort of science meets the press these days. I think that's a very interesting and quite tricky dynamic where with press and the internet and things can get sort of around the world so quickly, sort of if a scientist takes sort of too wacky an idea that they sort of haven't quite proven to the press, then all of a sudden the press can run with this headline and it will sell and it will go around, and you can start getting this sort of people believing that a scientist knows that aliens are on the moon type thing around the world because of an offhand comment or something. And I think there's sort of, I sometimes feel there's almost, you have to be, when you're doing a press release or when you're sort of speaking to the news, sort of trying to be a bit guarded to try and guard against this sort of sense of throwing misinformation, or not quite that, but sort of these wacky ideas out into the world. And that's tricky these days. And sort of I want to be able to sit in my office and sort of try and think about sort of, how could these planets have formed? Is it in a long-lived disk? Is it a new formation mechanism? Where are they coming from? But to actually put that into a publication and to put that in front of peer review, then sort of, we have such an ability to get data these days. There's almost then a sort of press from sort of peer review to actually go and get that data. It's like, you have this theory, we have techniques now to prove that or disprove that. Go and do that first, type thing. And so potentially that's sort of something that's playing a role in that these days.
Yeah, I mean, I hear where you're coming from, where there's an expectation of having done the legwork before saying something out loud. But there's also lots of things that it's not yet possible to do the legwork for. And I think about this in terms of, again, microbiologist. I always think about things in terms of biology. There was this really incredible author. His name was Thomas Gold. And Thomas Gold, a really long time ago, like in the 70s, wrote a book called The Deep Hot Biosphere. And it was also a PNAS paper, but he basically laid out this idea that, hey, I think it's possible that the biosphere isn't just on the surface of the Earth. I think that it's possible deep down. And everybody was like, oh, Tommy, you're so, how absurd. Because there wasn't any way to tell, right? They would sometimes dig microbes out of boreholes for oil wells, but they would be like, oh, they're contamination from the surface, and this is just kind of nonsensical. And then now there's an entire field that studies the deep hot biosphere because the tools have gotten to be sufficiently advanced that we can actually look, and we've developed tracer mechanisms for being able to show that the cores aren't contaminated and the stuff is actually down there. We can do metagenomics where, without having to culture anything, we can look at the DNA that's down there. But the only reason that field exists is, I think, because Tommy Gold wrote the book and was like, hey, what if? And I worry that and it's the epitome of 1970s kind of theorizing, free it just open and no concern for the consequences, no concern for respectability, just ideas. And I feel like we lose that now because our tendency is that we have to be so careful about the things that we say, because if we can't prove it, we can't say it. But I'm like, shouldn't we be making theories for 50 years from now, for 100 years from now, where when we finally can look, because that's how you lay the groundwork for where people will look 100 years from now. They're going to look back on some idea that was popular and they're going to be like, Bryant did have a really interesting idea. Like, we should check that out now that we can.
Yeah, no, you make a really interesting point that, potentially there is some sort of onus on us to be sort of putting these ideas out there. And there are sort of talking about biology, talking about life, sort of that's links quite well into a lot of the planetary science and where it's going now, trying to sort of find this life see if we can find sign of life on other planets. And there's also a lot of people, as well as just looking into, obviously people's first thought is to look for sort of a biosignature that would match into life on Earth as we expect it. But then there's also people beginning to sort of speak up and go, well, why are we assuming that it's anything like Earth life? Could it not be like Earth's formation of life seems to be lots of fairly random decisions throughout history to get us to where we are, and we're in a very particular part of space, distance from our sun, and potentially we should be not limiting ourselves to thinking, well, it's just human-like life out there. Maybe there could be some other form of life out there, and we need to keep an open mind into what we're looking at. And there's also people thinking about, there was a paper recently with some people beginning to think about if you were to have a planet around a red star that has a different set of light, different spectrum of light coming into the planet than the sun, how would that affect what photosynthesis could happen if you had a completely different spectrum of light? And I think there's some of these questions that are beginning to be asked to some extent, maybe not fully in this sort of quite wide-ranging, but there's some questions that are beginning to be asked about, okay, what could we be looking for when we get these sort of big telescopes online in 20, 30, 50 years?
Mm-hmm. Shilo has a question. No, go ahead. Are you sure? Extraterrestrials.
Yes.
Where do you sit on this pressing issue?
My feeling is that, so we've looked at the data and we know that I think on average people have worked out there's, at least from what we can see, roughly as many planets as stars in the galaxy, and there's 100 billion stars in the galaxy and billions of galaxies. And so I think if we were the only planet with life, that's almost scarier than there being other life out there. And
absolutely.
so yeah, that's where I sit. And I think I almost think that, yeah, it would be unbelievable if there wasn't extraterrestrial life somewhere in the galaxy, in the universe, whether it's in the solar system, not sure. Whether we'll ever have contact or have proof of it, I'm not sure either, but I think it must be out there somewhere.
Well, I agree with, because I mean, honestly, the question of what life is and how it emerges. From a
statistical standpoint, it's hard to imagine anything else.
Right, and I have a very seemingly clear picture for myself of the emergence of life from non-life and the inevitability of it. And so I'm just kind of like, look, the idea that it could become so complex and so absurd, the fact that we're sitting here talking over Zoom about the nature of life, like, I don't know that happens that frequently. Yeah. But I mean more in terms of, do you follow along with any of the UAP stuff and we've seen aliens are here on Earth and they're visiting and they're about to like release, they're always on the verge of releasing proof?
Not quite that far, no. I'm not sure if we've ever been visited by anything. But yeah, I don't buy into that too much.
Is that kind of the temperature of the astrophysics and astronomy community in general, that they're very skeptical? Because it's hard to tell from the outside how credulous people are that are actually spending a lot of time staring at the stars and distant planets. Because clearly there's a huge contingent of people that are like, no, they're here. But I inherently am very suspicious of that. And so I wonder, because the interesting thing about Beatrice is that she's associated with the Galileo Project and also with Avi Loeb. And so there is this entire the extraterrestrials are here aspect of it, where she's like, I'm going to look next for extraterrestrial objects in the solar system and then see if we can get funding to go retrieve them. Where I'm like, I've seen how that movie ends and I'm not sure. But she's dead sure. And so I wonder if that's something that comes across when you're just, talking to people.
Yeah, I think, just from sort of talking with people sort of within the community, I think, the general feeling, at least for me and most people, is that we probably haven't been visited, and there likely aren't extraterrestrials walking around among us today. But I think it's more of just a don't believe it. I'm not really sure what more.
Yeah, we had Diana Pasulka came on the show, and she's a scholar of religious experience, and she got sucked into the whole extraterrestrial UAP phenomenon as a professor of religious studies, and she's like, this is functionally, socially, psychologically equivalent to religion. And the structure of the communities is the same, and the passing along of observations is the same. And so academics tend to be pretty a-religious in general. And so it's kind of interesting because I think that within the academy, the preference and appreciation of the aliens are here narratives are much lower than they are in the general population. And I think it might also have to do with the sort of increased levels of atheism maybe in the academy, where it's a mindset that prevents you from this sort of unfounded belief. We're very evidence-based in the academy.
Yes, I think it's definitely that. We get a lot of people who are very evidence-based, and if I can't sort of put a number to it, if I can't get some proof of it, then I'm going to struggle to believe it's there. I think there's a lot just by nature of becoming scientists. We're all very sort of evidence-based and like testing and like facts and like numbers. And I think you're right. That does lend to some extent to that sort of, well, there's no proof of aliens, so they're not here. Although, whether that's then a case of you haven't proved it, but you haven't definitely 100% disproved it either. And then again, that gets into an area of, well, I mean, I personally don't believe they're here, but again,
and from an engineering,
if we're sort of stretching that sort of belief of sort of where things could go, I mean, we have no proof of them not being here.
And from an engineering standpoint, I think a lot of scientists are looking at this like, if we were going to go explore other star systems, we wouldn't send a space shuttle, probably. We would send some tiny little robots to go and take pictures and beam it back or whatever. It'd be much easier to do remotely, essentially. We're already figuring that out in our own solar system. And so that's kind of where my mind goes initially. I'm like, why in the world would they send little fleshy beings here to crash in the desert in New Mexico when they could just send a little tiny nano drone or something? It just doesn't, it's hard for me to understand. But I think people see what they want to see to some extent.
It's almost guaranteed. One thing that I wanted to ask is, okay, so we had Lee Cronin on the show a while ago, and he has this assembly theory of life, which is that the definition of life is that which makes complex molecules in abundance. Because there's a possibility space for the number of steps that you have to take in order to create some kind of complex molecule. And if you create that molecule specifically and in high copy number, it means that you have evolved a system for producing it as opposed to just random chemistry that comes together. And so once you have these high molecular weight substances that you have lots of that you can detect from a distance, that's a reasonably believable readout for spectroscopic detection of life. Right, so you can look at the atmosphere of a planet that's across the galaxy, and you can see high abundance of a molecule that isn't just elemental hydrogen. Right. And then you're like, okay, that planet happens to have a tremendous amount. He uses in his paper, he did it with Sarah Walker, they use the example of Taxol, which is a molecule that's used for chemotherapy, but it's derived from willow bark. And, the combinatorial likelihood of it being produced accidentally is unfathomably small.
Yeah.
And so I wonder if people have started applying his complexity theory model for looking at spectroscopic evidence from these distant planets for stuff that's not just, carbon, hydrogen, oxygen.
Yeah. Yeah, no, I think definitely in terms of sort of looking at these atmospheres of other planets, I think the people who are sort of more in the field of looking at these to try and find sort of biosignatures and sort of these signs that there might be life on a distant planet are definitely, their focus is looking for this sort of disequilibrium, sort of these molecules that can't have just formed through some equilibrium process, like there's either too much of them or there's two molecules existing together, which would normally sort of cancel each other out, obliterate each other if they were just left alone in a vacuum. I forget exactly which two it is, but I remember there was a pair of molecules, I think just involving sort of carbon, oxygen, and hydrogen, maybe. It's just a pair of molecules where if both of them were seen in an atmosphere in high abundance, then could be construed as a biosignature or marker that there's something going on, because these molecules wouldn't exist in an equilibrium by themselves. So at least one of them or both of them has to be continuously produced by something. And there was even sort of not for life, but there was one of the first planets that was observed by JWST. They found a significant amount of, I can't remember, I think was silicon dioxide. They found, I believe that was the one, but whatever it was a molecule that was produced through photochemistry. So they had this sort of first detection of photochemistry in an atmosphere through the presence of this molecule, when this was sort of the pathway through which it could be produced in that quantity to then be observable. And so, yeah, I think people definitely are, if I understand what you're saying correctly, I think people are definitely sort of looking to sort of put this through, well, if we look at an exoplanet atmosphere and we see something that can't exist in sort of an equilibrium state, must be being produced by something, and that could be a first sort of smoking gun almost, that there's something on that planet, be it life or be it something that's producing these molecules in these large quantities.
That's very cool. I mean, it's I feel like we have a hard time even really telling in our own solar system. And so I'm a little suspicious of being able to do it for stuff that's super far away, but the idea is nice.
Yeah. It's a nice idea.
Yeah.
So what's coming next for you? You mentioned potentially collaborating with people modeling these disk formation. Are you going to keep cruising on this discovery that you've made, or are you going back to the original data and looking for more anomalies? What do you imagine for the future of your next 30 years? Yeah.
Well, perhaps not the next 30 years, but definitely the next sort of few years. I think one thing we'll be trying to push forward, at least with this modeling and getting some further observations of these planets that we have found, to try and begin to sort of piece together a more complete picture of where these planets could have come from, how they could have formed, try and really interrogate that side of the theory side of it more for these discoveries, these new planets. That's part of what will be coming next, to really try and figure out if we can start pulling some real stories and backgrounds to these planets. And then also in terms of my sort of other sort of work going forward, I was sort of going to be similar in terms of sort of how sort of the star sort of affects the planets. So that's all what I'm quite interested in, is sort of what planets we see and how the star affects that, and that I'm actually beginning to look at sort of how common look for planets around these sort of evolved stars, so sort of subgiant stars that are beginning to evolve off the main sequence and expand and increase the tidal interactions. Because as I was mentioning with the white dwarfs earlier, we think that these planets, as the stars evolve, they start destroying and engulfing planets, and planets start spiraling into the stars. And so I'm wanting to try and see what planets we can find around these, and then if we can look for planets around these sort of evolved stars, we can then hopefully see what planets aren't there anymore, so we can compare it back to the planets we see around sort of stars like the sun in the most of their lifetime. And by making comparisons, we might be able to actually start seeing or start learning, getting more of that evidence of planets being engulfed by their stars, planetary systems beginning to die as the star evolves. And that's also where I'm going to be putting some of my sort of focus over the next few years sort of into that, which should be very exciting.
Very cool.
Nice. Well, I look forward to seeing you in the headlines again soon, sir.
Do you have any closing thoughts?
No. My mind just went completely blank.
I mean, I think that it's really cool work that you do. You look into the most difficult to see corners of the universe, and you try to piece together what might be happening, what might have happened. And it truly is very mysterious, and the possibilities seem like they might be weirder than we think. And so it really seems like you're in the start of a career that is gonna go to some pretty wild places.
I really appreciate you coming by too, because I tend to email as soon as I see something like this. Like I'll just every morning I read through the POP I'll go through phys.org and all these different sites, and whenever I see something that's doesn't fit into the landscape, I always email these people, hey, come talk to us. So I'm really glad we got to sit down with you and hear what you're working on, and I really appreciate you coming by. So thank you for giving us your time.
And entertaining our far out ideas.
Yes.
That's all right. I feel like, we could do with some more, potentially could do with some more far out ideas.
Excellent. I like that. I appreciate that.
Well, yeah, let's touch base down the road. You know, when you start working on your next project, send us a note when you have stuff that you want to talk about.
Yeah, we'll do.
Excellent.
Right.
Thank you so much.
Thank you very much for inviting me. It's been fun.
Thank you, Dr. Bryant. Have a great rest of your day.
Thank you. Bye. See ya.